So we were looking at genetic algorithms. So as you can see up to this point, you have many parameter operator choices available to you. For the numerical values, you have to decide on the population size. So far there is no strict rules for population size, and population size is usually difficult to adapt as well, almost impossible to adapt. But in recent times, for real coded problems or real valued problems, people think about starting with very big population, initial population, and then downsizing it along the evolution. So that seems to be working better for real variable optimization. And then you have to find the set values for mutation, and you have to set values for crossover and so on. These are common parameters in genetic algorithm and all other evolutionary algorithms. Mutation size is usually the mutation probability is usually set so that you will flip 1 or 2 bit strings. So if your bit string is, if your solution is 10 strings long, 10 bit string long, then the probability may be 1 over 10, something like that. So you try to flip 1 or 2 like per solution. Crossover rate, we don't really have any specific rule. It can be problem dependent as well. Apart from the numerical ones, you also have to decide crossover, which one you want to use, 1 point, 2 point, uniform. There are so many different crossover operators. And then selection, parent selection, which method you want to use. Then once you have the offspring parent combined population, which method you are going to use. So again, you have lots of choices. So
is there any criteria on the choices, like for example, operator, which one will be better? How do you choose?
In the past, people do lots of trial runs. Exhaustive search. Change this, work with this combination, work with this combination. So the design of experiments type of things. So design of experiments type of search people have done. But then in recent times, so no general theory to deduce. So when the problem is given to you, you cannot just say this operator is going to work, this parameter value is going to work, and all those things you won't be able to say when the problem is given to you. But for an alternative for the exhaustive search is adaptive methods with ensemble of operators and parameter values. So what you can do is you can try with a few operators and few parameter values and just label them. Okay, this one is working okay, this one is not working, this one is working okay. So you do a few trial runs and select some of the operators. If you have 10 operators, we don't want to include all 10 of them. So you select 3 or 4 better ones. And then for the parameter values, you pick few suitable parameter values. What you can do is you can put them as an ensemble in your memory. What we do later on is adaptive, you can do adaptation. How do you do the adaptation? Based on performance feedback. How do you get performance feedback? Your evolutionary algorithm is going to run from generation 1. So you are going to start generation 1 and then 2, 3, 4, 5, 6, and the generation counters may go to hundreds or thousands generation. The population is going to evolve. So what you do is initially you assign one particular operator for crossover, one particular operator for selection, one particular parameter value for crossover, one particular value for mutation. You generate offspring. Look at the offsprings. Are these offsprings improving from their parents? If they are improving, you give credit to these operators and parameter values you used. So along the way, you give credit to operators and parameter values that are producing better solutions. So along the way, you learn which one is doing better. Even for this method to work, you cannot just bundle all the things together. You cannot bundle. You still have to do some trial runs. You have to do some trial runs and then apply the ensemble with adaptive method. Ensemble means multiple operators, multiple parameter values for one operation. Crossover, you give few different operator selection choices, few different parameter value choices, and then apply the performance feedback based adaptation. And this one can work for different problems. So when you change problems, you can still use this general approach. So it will eliminate the exhaustive search over so many operators and so many values. So in recent time, almost all our algorithms are adaptive based. So if you develop an algorithm without adaptations, very likely it will be underperforming. And the adaptation based methods are very likely to perform better. So the adaptation based methods I will explain little bit tomorrow with differential evolution. So differential evolution, with differential evolution I will go a bit deeper into that method. Then with that I can explain adaptation, but the principle is just I explained to you now. But then again there are lots of variation, how you give credits for better performance and so on. So the earliest theory for genetic algorithm is schema theory, I think coming from late 70s I think. So Holland tried to explain the schema theory and why GAs are working and so on. But in recent times, people say the proof is not perfectly correct and it may have some errors and so on. So not sure about those details. So you can check the schema theorem and so on. So some people say the theorem is not correct. So the proofs are not correct and things like that. So not sure.
Where was that published in, the schema theory?
Maybe in his books, I think it's 70s. Maybe there's no journal and is it?
It's a book.
His book.
Himself.
Himself. By himself, I think. So he has a book.
Schema theory has been, in the early stage of John Holland's
Book. I think he has a book.
And the building block theory.
Oh yeah, that's right.
Those two are the only formal. In my personal view, those
For-
two are the only formal theoretical work.
For the genetic algorithms, yeah. And then the schema theorem, people say it's not correct, I think.
Theory and schema theory.
30 years ago.
Maybe more than, I think 40 now. Now 40 something. Another reason maybe that people are moving away from the binary genetic algorithm after 1985 and things like that. So not many people are doing serious work now in binary genetic, I think. So we will look at evolution strategy and little bit of particle swarm optimization. Maybe the differential evolution I may skip little bit because tomorrow I'm going to cover it. Maybe I just cover everything tomorrow itself, I think, just instead of doing little bit now. And these algorithms, some of these algorithms I am also not very familiar with. I got the slides from my friend, so maybe we can read together, I think. And I don't have much interest in so many methods because there are so many different names and so many different methods, and the methods haven't been well benchmarked, not well evaluated. And as I told you before, there are thousands of journals and hundreds of conferences looking for papers. So people are just writing and publishing. And then it's if you want to read and understand all of them, you are giving too much work to yourself also, I think. So until they themselves, authors themselves, do a rigorous evaluation and then highlight it is really good, it can beat all these methods, outperform all these methods, then maybe we can go into them, I think. So the evolution strategy is one of the original methods. As you can see, it is coming from 1960s, so it's before genetic algorithm as well. So this is the genetic algorithm that we looked at just now is for binary decision variable 0, 1, and this one is for real variable optimization. So if your decision variables are real valued, then you can use evolution strategy. But the one I described here is the basic version from 1960s. So the steps are anyway pretty much the same. Randomly generate initial population of M solutions and then compute the quality of these M solutions using the objective functions. Use all vectors as parents to create same number of offsprings or a specified number of offsprings, and the original method was Gaussian mutation. So that is the original one. So when you talk about Gaussian mutation, you have to specify the standard deviation. So that is a user specified parameter, standard deviation. Then you have to calculate the fitness values of these offsprings, and then you have to prune the population to the original size, capital M. So again you have variations. People have replaced this one with other values, other distributions and things like that. Levy distribution, Cauchy distributions, all these distributions have been considered. Then how to adapt this one, the standard deviation parameter, how to modify this one, people have looked at. So you go through the step anyway. So this is the iterative step. Mutate the current population, evaluate, and then downsize to the capital M population size, and then go and generate offspring, evaluate, downsize to capital M. So when you downsize, you are looking at the fitness values. The easiest one may be you just rank all of them and take the best ones. So this is the greedy type operation. You select the best ones. So that may take you to local convergence. So you, in the end, when you have exhausted your given computational resource, or when your solution is of satisfactory quality, you stop the iterations. And for the evolution strategy, this is the most competitive state-of-the-art variant. So if you have a real variable optimization problem and the dimensionality is not so high, say 10, 20, things like that, then CMAES is a competitive candidate for you to look at. And the software is available in MATLAB format. So there are few variants, but almost all the variants are available in MATLAB format. And this is a competitive real variable optimizer, CMAES. And it works very well when your decision variables are linked. So there is a linkage between your decision variables, where the line search and optimizing one parameter at a time, one decision variable at a time doesn't work. Then you can make use of this CMAES. So you can try this CMAES. It's easy to use. Recently there was a paper submitted to our journal, Swarm and Evolutionary Computation Journal. The title of the article is the variation between CMAES algorithm and its software implementation. So what they are saying is, and my students also told me many times, the algorithm is fairly different from software implementation. So the algorithm is presented in a nice format, but the software implementation has lots of tweaks. So suddenly you will see a number 2 or 3 appearing there, and no one knows why it is there. So then someone decided to write a paper on it. The CMAES algorithm and its software implementation is under review now. Let's see what the reviewers are going to tell about it. Covariance matrix adapted. So the covariance is the one that is going to de-link the decision variables. So when the decision variables are linked, related together, other optimizers may have problem because they may do decision variable wise search. Some of the optimizers do one decision variable at a time search. But when the variables are linked, decision variables are linked, you may have to move them together in a particular direction or orientation or something like that. So the CMAES is doing the delinking, covariance matrix adapted evolutionary strategy. So if you have real decision variable optimization problems, you should consider this one as one of your candidates to evaluate. So differential evolution, just tell you the first slide story. So it is coming from 1995. Even the next year, it participated in the competition at evolutionary computation conference in Japan, and it finished third place. So immediately after introducing the basic version. And the another reason I have very good opinion is that I have been running competitions at IEEE Congress on Evolutionary Computation from 2005 to now. So over all these 13 years or so, the number one has been almost always differential evolution. So you take any problem instance, multi-objective, dynamic, single objective, multi-modal, constraint, take any of them, the differential evolution is there at the top. And by the way, I have to tell you this, the CMAES I highlighted here, it is very good for single objective bound constraint. So only for that case it is very good. Single objective bound constraint, real variable optimization. Only for that case you should look at this one. If your problem is anything else, maybe don't look at it. It doesn't work well. For multi-objective, constraint and all others, multiple solutions, for all other cases it doesn't work well. And these are correct for the original algorithm. Easy to implement, it is true for the 1995 version, but the recent variants are fairly complicated. So the recent variants, you may not be able to reproduce them unless the authors are giving away the codes. If you try to recode the recent variants, the results won't be what they report in the papers. And the control parameters, now they have increased with the recent variants, there are more control parameters. So even though control parameters are increased, they are mostly adaptive nature, so it is not a problem. So earlier you had 2 or 3 control parameters. These control parameters are very sensitive. If you change here and there, the performance varies significantly. But people introduce more control parameters and make them adaptive. So the newer control parameters are less sensitive because they include with adaptations. So they are less sensitive now.
So which are the two algorithms finished top?
I don't remember. So it's 96, maybe I am not in the field also, I think. Just finishing my PhD in pattern recognition and neural networks. So I came into evolutionary computation from 99 or 98, 2-3 years later. So, but anyway, even the top ones may not be state of the art anyway now. If you look back, it's 20 years something. So this is differential evolution. As you can see, initialization, mutation, crossover, and then the parent offspring selection. So with this, we can move on to the next one. So okay, so I will come back to this tomorrow. So we will look at particle swarm optimization. There may be some talk as well. Anyway, but for this one also I give only 2-3 slides, not many here. So this is also coming from 1995. Differential evolution was also introduced in 1995, but the differential evolution didn't take off rapidly. The explanation is simple. The inventors of differential evolution, they didn't stay in universities to promote differential evolution. So after publishing 2-3 papers, they didn't do anything. Then some other researchers have to identify it slowly and then improve it and then identify its performance. Then it became popular. So from 96, 97 to about 2005, there is almost no journal paper on differential evolution. So it's about 10 years like without a journal paper and few conference papers. Whereas particle swarm optimization, it became popular rapidly because one of the inventors from university. So he has been going around to conferences and presenting this method, particle swarm optimization. So I attended their discussion session in 1998 at the conference, World Congress on World Congress on Computational Intelligence in Alaska, Anchorage, 1998. So they were sort of announcing about this. Actually, I was at the same conference when they published the first paper in Perth, 1995, International Conference on Neural Networks. Is that right? So in 95, they published it in Perth. I was at the conference, but I didn't attend the session. So I didn't get to know this one in 95. But in 1998, when they organized an information session, I went there. I sat in the session and then went back to University of Queensland and immediately did some simulations and published a paper the next year, 1999. So when I published my paper, mine was about the 15th paper or something in the particle swarm optimization. So being one of the earliest papers, it had high citation now. So about 1,000 plus Google citations.
But now you move on to DE.
Differential evolution, yes.
You use PSO as much.
Sorry?
You don't use PSO as much, right?
Nowadays, no. I think it's the performance comparisons. And I showed you this this justification. PSO is difficult to see in any of these competitions as the top performer. So we don't see them for the difficult problems. So the competition problems are really difficult problems. So the method has to be very good. But when you look at the real world problems comes they come with different difficulty levels. Not all of them are very, very hard. The competition problems, all of them are very difficult ones. So real world problems with different difficulty levels. So some of the easier problems you can solve with these swarm methods and all those things here. You don't need really an effective one to solve some of these problems. So it emulates flocking behavior of birds, fish, school of fish or whatever to solve optimization problem. Each solution in the landscape is a particle. So that is where they start with a particle swarm. So the particle can represent your bird or fish or whatever. So here we are showing the birds anyway. Each particle has a fitness value and they also have velocities as well. So this is a motion based. And usually the motion based, dynamics based methods are not so good compared to differential evolution, because most of the dynamics based method, they take the next point 100% of the time. So you allow the bird or fish to move to the next point and then you take that point even if that point is very bad solution. So all dynamics based methods are like that. So that is a disadvantage of PSO and other swarm based method. I think almost all swarm based methods are they come with these analogies. So when you say your bee is flying from here to here and the solution is bad, you cannot say reverse. So you cannot tell the fish or bee or bird to reverse back. So they just go and stay there, whereas the differential evolution is selection based. It generates a new solution. If the solution is not good, you don't take it anyway. So it doesn't have this analogy of forcing you to take And the velocity is also another problem. It is usually very difficult to control. So that control is very difficult. It's a dynamic behavior, also very difficult to control. So in addition to these two disadvantages, then you have another disadvantage, the loss of crossover. Almost all swarm algorithms don't have crossover, and that is also bad. So in the last few slides, I will explain briefly why that can be bad as well, no crossover. So the swarm algorithms have all these disadvantages, in my opinion. That is how I explain why they are not competitive for the difficult problems. But then they can solve real world problems if they are not so hard anyway, not so difficult problems, they can still solve them satisfactorily. And in some cases, the swarm methods may be better than differential evolution because differential evolution is prepared for highly multimodal difficult problems. So you are using a more powerful method to solve a simple problem, so it will take more time to find the solution, whereas these methods will find the solution faster for easier problems. So when you compare with easier problems, sometimes these methods may look better for you compared to differential evolution. So the PSO has two equations. One of them is the velocity equation, velocity update equation. Other one is solution update equation, the new point. So as with all other swarm and evolutionary algorithms, you are going to initialize your particles or your solution candidates in the search space. And most of the time it is random initialization. So you are going to initialize your population randomly within the search space. With the initialization, you are going to have the initial positions as well as you are going to have initial velocity. So the velocity also has to be initialized within the limit. So they have some limits for the velocity as well. So once you do the position initialization, you can perform the fitness evaluation. With the position information, you are going to do the fitness evaluation, and then you can identify the best solution in the population. So the best solution in the population is identified as global best. And the personal best is for each particle, each solution candidate, you assign a personal best, the best solution the particular particle has found so far. So that is known as the P best. So you have P best solution and G best solution, and the velocity update equation is something like this. So these are random values. C1, C2 are the two parameters. You have to tune or adjust C1, C2. These are randomly generated 0 to 1. So basically you are moving the particle towards the global best solution and the personal best solution. Somewhere in between you are driving the particle. So this is velocity update and this is position update. So position update is done by adding the velocity to the previous position. So this, if you want, you can include a generation counter. The generation or iteration counter is not there. So this is current position, you add with the velocity, you will get the next position. Okay. So the global best version of the PSO implementation is very greedy. It converges very fast and most of the time premature convergence to a local solution. Convergence means the differences, all these differences will become near zero very rapidly. All the population members are just at one point. So they introduced local best. The G best is replaced by local best. So you don't select the best from the whole population, you select the best from a local neighborhood and then do the dynamic equation.
Quick question. So you have this swarm of particles, and one of them is doing right now the global best, right? So from your like population dynamics, the global best basically doesn't move at all. Because like I mean the
But you have the velocity. The velocity is not zero.
But I mean, if you're already, like for the particle that's already at fast, the velocity because it's also, it's both its personal fast and also like the global fast. So like the velocity will be zero. So I'm just, wonder, do you have another random forcing at n?
The global fast is determined at that particular time point. This is the best way so far.
Yes.
And after that, they will still continue to fly individual particles, and then they will find a better, lower solution.
No, but
if they
I'm
can do it.
just saying, like, if you're already at global, like if you're the fast among your friends and you're not moving, because like based on the equation, I mean, unless like some of the friends who are approaching you that will find some point better than you, then you will try to move there.
But they're always moving. They're always
They're
moving
moving,
at
always
each time.
moving.
Yeah. So each one might discover something better, and then they negotiate about it. Okay, maybe the global optimum is a little bit away. So it's a dynamic process, and you can stop it after a number of iterations.
So this stagnation, the stagnation may not last maybe one iteration or two iterations, because you have other population members. So if the stagnation may be only for one point, but if the G best is sitting there for a long time, then very likely all others will go to that point, and you have premature convergence. But otherwise, this low velocity update and all those things will be only for few iterations. But this is the first version anyway. But this equation is now rarely used. I think 1 or 2 years later, the inventors said, don't use this one. So they also say it is a bad one.
Take away the velocity equation.
They have momentum. They put the momentum term to the velocity. So momentum term means this one cannot become zero. You take about 70% of the previous velocity. So even if this one is zero, they have added another term. About 70% of the previous velocity, you are going to take it anyway. So, so this original version, I think you are correct. The G best may stay there until other points find a better solution. Then this one will move and things like that. But that one they fixed it within 1 or 2 years. Then they have this local best. So this problem is identified by many people. Anyway, the search behavior of the first version is not so good. Then they replace the G best by L best. So this is what they encourage us to use, and all of the good PSO versions are local best based. The G best based is not used. So the parameters and the notations are defined here. So you have P best, G best, L best, and all those things. All these are actually the solution candidates. And with each solution candidate, you have the fitness values, how good the solution is, and all those things. So I think in this set, I didn't put any other improved PSO versions, like the momentum based, constriction factor based. They are the improved ones. I didn't put any of them in this slide. They are in some other slides. So anyway, you get my point anyway. The momentum based means you take 70% of the previous velocity and use it. So the particle is certainly going to move anyway away from the current G best position, because the velocity is coming in from the previous iteration. So these algorithms, I didn't pay much attention to them. So I will briefly flash through some of the slides. You can look at them. But my suggestion is that don't waste much time with all these methods. There are so many of these methods. So you should just go to some of the best methods to solve your problems, I think. But researchers have a problem of publishing papers. Like I have a particular practical problem. This problem has been solved by using PSO, DE, and all these methods. but no one has tried harmony search. So what is the original work you can do? Take the same problem, apply harmony search, and then submit a paper and then say no one has done it. No one has applied harmony search to solve this problem, or no one has applied water cycle algorithm. No one has applied Jaya algorithm to solve this problem. So for a particular problem, you keep on applying, you come up with new name, and then you have all these problems, and then keep on applying different algorithms. So if you do strict comparisons with best methods from the literature, usually difficult for these new methods to pass through. But some of the reviewers and some of the journals accept comparison along one line. One line comparison means you compare only with differential evolution, don't use anything else, or compare only with particle swarm, don't use any of them. So when you do one line based comparisons, new names are very friendly. So when someone proposes a new name, imperialistic competition algorithm or something, there's ICA or something, is that right? So when someone proposes a new name, then you can say I am applying this particular method to solve this problem, and no one has applied this method to solve this problem. So I am not comparing with anything else. So trying to publish it. So with the new names, you can do all these things others have done with older methods. So whatever researchers have done with all these methods, you can come up with a new name and then you repeat all of them and don't talk about these methods. And there are journals and conferences, they are happy to accept them anyway. So someone told me this Jaya algorithm, do you know what is the motivation behind Jaya algorithm? Can anyone guess? Someone told me motivated by the inventor's wife. Wife's name is Jaya. That is what someone told me. So the algorithm is coming from India. Then someone told me, do you know why he called this Jaya? His wife's name. So he says this is an algorithm with no control parameters. So maybe that is the nature of his wife, cannot be controlled. So I have an optimization algorithm with no control parameters, like my wife. So that is also nature-inspired algorithm. But I don't know whether it is true or false anyway, but someone told me anyway, so like that. So this is harmony search coming from harmony or music. So I don't understand music much. So they say you put these nice sounds together to compose your solution, something. So nice sounds. They have all these terminologies. So some of the terminologies are here. Musical instrument, pitch range, harmony, aesthetics, practice, experience, and all those things. Experience means past experience. So they map it to your optimization problem and solutions. Okay, so this is what I mentioned, that this harmony search algorithm was discussed in this particular paper, metaheuristics, the meta for ex post. So in this paper they say it is very similar to ES, no difference. If you do some parameter settings right way, it will become ES or something like that. They showed how it is mapped from harmony search algorithm to evolution strategy. Of course, the storylines are fairly different anyway. It's coming from music. So as I mentioned to you, many of these nature-inspired algorithms, the narratives are fairly different, but when you write the equations are very similar to previous methods when you look at the recent ones. So HS operators, random playing, memory consideration. Actually, the harmony search is not so good for real valued optimization. Their performance is not good, but they are okay for combinatorial optimization. The reason why they are okay for combinatorial optimization is that in combinatorial optimization, the real work is done by local search heuristics. So the real work is they are by local search heuristics. So when you apply different swarm and evolutionary algorithms, you may not see significant difference in performance. They all perform reasonably well. So this is very difficult to get the analogy. I didn't pay much attention, but just give you the picture. So water cycle algorithm. So water cycle means the water evaporates and comes back as rain and so on, that kind of water cycle, and then it goes to streams, rivers. So the names are on the next page. So this is the publishers, computers and structures. Is it a good journal? I am not too sure, is it? Anyway. So this is the analogy, water cycle. Then they have all these words: precipitation, streams, rivers, sea, surface. I don't know. I don't quite understand anyway. So you read them. If you are interested, you can have a look at them. So the equations are here, but if you look at the equations, they look very similar to differential evolution or PSO and so on. So that is where the problem is. All these methods have similar update equations eventually. So this is JA algorithms. So the promise is that it has almost no control parameters. Just two, R1 and R2 are the random numbers generated 0 to 1 range. So that's all. So you just randomly generate two numbers and then you can do the Jaya iteration. So this is the algorithm, so you can have a look at this. So this kind of scheduling problems, even though they talk about harmony search, water cycle algorithms and all those things in the title, the real work will be done by some local search heuristics inside. So that is where you have good performance eventually. Then you have ABC, group search, cuckoo search, firefly and so on. So maybe I allow you to look at all these things yourself leisurely. Is that okay? So B is about nectars. Then you have the scout bee, worker bee, queen bee and all those categories. And then how they convey the information, waggle dancing or something like that, is it? So they have some, it's all coming from the bee terminologies. Okay. So you have dance floor, beehives, all the so then when the equation comes, it's again PSO differential evolution, not so much difference. The storylines are different. Cuckoo search algorithm. So it's about cuckoo bird. So it's introduced by, I think I gave you his homepage. I think he has several methods like this. So this is one of them, cuckoo search algorithm. Group search, this is about hunting behavior of animals as well, how they hunt for food and things like that together and so on. So producers and rangers and all those names coming from the animal kingdoms. So you have all the names anyway, lion, cat, swarm, lion, swarm. So yeah, the equations have the same problem anyway, fireflies. So a couple of slides I have on similarities and differences. So most of the swarm algorithms are like this. So when you look at this, these are more like a dynamic type of equations where you don't have crossover as well. So if you look at the basic equations of many methods, most of them are like this. So they all are similar to differential evolution and PSO when you look at the details. So this is DE is similar to ABC with some CR value set to 1. It's the similarity between differential evolution from 95 and ABC from 2004 or 2005. So 10 years later you have ABC algorithm. Then cuckoo search algorithm is similar to evolutionary programming from 2004 or 2003. So cuckoo search is done about 6-7 years later. So that's similar. So you have lots of similarities anyway. So some of the similarities are highlighted. So this is the take home message. Nature inspired methods have different storylines, but when you convert the storylines to equations, they become very similar to each other.
So in the cuckoo's algorithm, how does the Leibniz distribution comes in?
Not sure. I told you I had to read with you, I think. So if you want, I can check it later on and tell you. So there are so many methods like this. So I think I am not going to study all of them. So my focus is look at the most effective method and how to improve it. So that is what I am. So my students are looking at differential evolution only, how to improve it further. So until someone shows me an algorithm with systematic comparisons, empirical comparisons to show that it is beating the best of differential evolutions, until then I am not going to study this. There are hundreds of them. So anyway, we can check it out and find out how this one is coming in. So the Levy is again the mutation operator. So it's and it's similar to evolution strategy as well. So if you look at the equation, see the new point is generated by mutation. This is a mutation operator. Most of these methods are for real valued variable optimization, all real valued optimization. So you mutate and then get the next generation point. So that is where the Levy is coming in for mutation. So the hybridization methods. So if you are going to do hybridization methods, for the real variable optimization, I will discourage you for the hybridization for real variables, because I think this one, why I discourage you from hybridization for real variables is that if I review a paper where people hybridize 2-3 methods to come up with a new hybridized algorithm, I put one question: can you show that your hybridized version is better than best versions of the algorithms you are putting inside the hybrid? That means best version means don't compare with the 95 version or 2000 version. You compare with the 2015, 2016. So you are combining differential evolution and particle swarm, combining them together to come up with a hybrid algorithm. So I can accept this hybrid version if your hybrid version is better than the best DE in 2015 or 2016 and better than the PSO in 2015 or 16. Otherwise, why should we mix them together? If the best of the individual algorithm can work better, why do you want to mix 2-3 of them together to get worse performance? So if I put that question, most of the hybrid papers will not come back to me again for review.
Is there a standard test problem?
We have lots of benchmark problems. There are lots of them. I have been creating lots of them.
I think the comparing of algorithms, like as you just mentioned, the hybrid version method and the individual components. Comparing algorithm is a very, very tricky business, isn't it? I mean, like, how do you know that the tuning parameters you use for this is the right one? Maybe you haven't found the right one that can beat this one, right?
Yeah, we usually put this comment, we pass the comments to the authors, but then authors have the objectives, like I am developing a better version of DE. So my objective is to show that my DE is better, and the reviewer is asking me to compare with few algorithms. So I take few algorithms. As long as the other algorithms perform worse than mine, my objective is fulfilled. So I am not going to worry about it. When I will worry about it, if the competing algorithms are performing better than mine, then I will become worried. Then I will think how to improve my algorithm. So that is how people are doing research. So in the review comments, we put this query. Did you tune the competitive algorithm on the same problem set? Whether the competitive algorithms were tuned on different problem set. Are you just copying the algorithm and parameters from the published papers? In the published paper, did they use the same problems? So we ask these questions in the review process. So we try encourage them to tune, but authors, as I told you, the objective is to show the algorithm is better than others. So they may spend lots of time here and minimal time on the competing one. So the comparisons are usually not fair, I think. So that may be the reason why we are publishing so many papers. This method is better than all these things. Then you look at another paper, then that another author will say this method is better than this one, all others. So this kind of confusion is there. But the hybridization is very useful for the combinatorial cases. As I mentioned to you, the hybridization is very good for combinatorial permutation problem, local search heuristics with swarm evolutionary algorithms. Genetic programming, it is slightly different method, and I don't work in this method. But my understanding is if you have a symbolic regression task, genetic programming is a good method. So that is my understanding. So if you have such kind of problem, then you can look at genetic programming. I haven't looked at it. So this is the genetic programming is tree based, evolving trees like. So it can include functions like sine, cosine, multiply, square root, power, and all those things. So you develop equations and functions. Theoretical studies. So this is what I have, and I haven't done any theoretical studies myself. So I sent an email to Dr. Das, Suganthan Das. He likes theoretical studies. So he sent me some references, and this one I have stated anyway, my standard review question: can you demonstrate that your theory can overall improve performance of any one state-of-the-art algorithm? Can you demonstrate that you come up with a new theory? So when I review a paper, I put this question, and most of the time the answer is no.
What do you mean by improving performance?
So you are doing some analysis with the parameters. So you eventually can you come and say, if I tune the parameter this way, it is going to perform better. Can you say something like that?
So you want the analysis on the tuning parameter?
Whatever your analysis, is it going to improve the performance? So for evolutionary algorithms, swarm algorithms, we shouldn't be talking about convergence. There's no need to talk about convergence. So that is my argument. So convergence is not there anyway for evolutionary algorithms.
Is it part of the reason is this works so fast? I mean, you can just keep on trying and get a sense where it works?
Convergence, is it?
Yeah, no, I mean, this thing works pretty fast, right, most of the time.
But I have some explanation for convergence, why we don't need to ask for convergence. I explain later on. So I have some conflicting ideas later on. Maybe I can move on there, I think. So this one I mentioned, metaheuristics, they were developed as a complementary methods for mathematical programming methods. So if you expect similar rigor from this metaheuristic field, it is not very meaningful, justified for the starting point of your objective anyway. Your objective is, we want a complementary methods for this one, the mathematical methods. That is how we start. Then if you want to end up at the same place as rigorous mathematics, then something is going wrong along the way. So some papers are listed here, again emailed to me by Dr. Das. So I just put some of them here. So Shinyao, he also likes theoretical studies a lot. He has lots of theoretical papers. But most of the time, the theoretical studies are based on very simple versions. 1 plus 1 evolutionary algorithm, 1 parent, 1 solution. So it's no population to begin with. So when you take away the population, we are not talking about swarm or evolutionary. So there are some other theoretical studies you want to look at. These are with respect to PSO. With respect to PSO, you need only one theoretical study because PSO has dynamics and velocities. So when you have dynamics and velocities, when will it become chaotic? Is this going to become chaotic? That is the only one question I respect. It's a meaningful question to ask. And the answer is like the C1, C2, there are two parameters. The summation must be below 4.1. So there are some theoretical proofs for some simplified versions. And when you simulate below 4.1 and above 4.2, you can show it as well. So this is what I asked for from the theoretical studies. You come up with a theoretical conclusion. Can you show it, the effect of it in the state-of-the-art algorithms? So here they can show it. So some general thoughts. I just give you time to read this. So no free lunch theorem, is it really a meaningful theorem? So I would say it is common sense. So called as a glamorous theorem for common sense. Why do I say common sense? Because for me all these are no free lunch theorems anyway. Have you heard about panacea or something like that in medicine? No? You do the Google search, internet search. So this is Sanskrit word, I think, Amrita. Amrita, heard about? There are some stories about this snake and mountain and you no? So if you don't know, you go to this Bangkok airport, I think they have this. How you take the Amrita, this is the nectar of immortal life. No illness, no death and things like that. So panacea is that you don't have a single medicine to cure all illnesses. It is same as no free lunch theorem, somewhat similar. For different illnesses, you need different medicines. That means for different optimization problem, you need different algorithms. Different problems requires different algorithms. Practical relevance for no free lunch theorem. Is it practically relevant, no free lunch theorem? My answer is no, because no practicing engineer will be solving 50 different problems in 1 day or 1 month or 1 week or anything like that. So if you are a practicing engineer, you may be employed by one company like Honda. They will say, design me this particular component. So you are looking at only one problem, maybe for a long time. So when you look at one particular component and you are going to design minor variations of it, you can come up with very good algorithm just for that problem. You can tune it. So the no free lunch theorem, do you understand the academic relevance? Academic relevance is very high. If your algorithm is not best on all problems, so you are comparing with many other competing problems, you have a new algorithm. If yours is not good, then reviewers will ask, why is yours algorithm is not good? It's not beating all the algorithms. Then you say no free lunch theorem says that you cannot. Then reviewers will say, yeah, you are correct. So I have few slides like this. Convergence. So this is, I don't know whether mathematicians will agree with me, but anyway, if you don't agree, tell me. Do we really need convergence for evolutionary swarm algorithms? My answer is no. I think I would say if your algorithm doesn't converge, that is better. So convergence, why do you need? The convergence issue, it comes from single point based search methods that were there in the early stages, like from mathematics and so on. You get one point and you try to find the optimum solution. If you do single point based search and if your single point doesn't converge, you are going to end up with no solution. That is guaranteed. Is that okay? So if you do a single point based search, it has to converge. It cannot just jump here and there and everywhere. You said, okay, it has to converge, and you may have the differentials and all other things to guide it to the solution. But when you have a population of solutions, this is what I would expect. When you are solving a real problem, my suggestion would be that even after you find the global optimum, the population should be diverse. Why, if it is possible? And why I say is that when you solve a practical problem, most of the time you don't know where the global solution is. If you know the global solution, you don't want to solve it anyway. But, but we researchers solve problems with known solutions. So when we do research evaluation for the new algorithms, we make use of benchmark problems. And for all benchmark problems, we know where the solution is. So immediately we can say if the evolutionary algorithm converges to the known solution, we say it has done the work. If it converges to a local solution, we say it didn't do the work. But as far as the algorithm is concerned, it has no idea where the right solution is. And it is the case when you solve a real practical problem. So when you work with the population-based methods, can you have the diversity? Are you able to control the diversity of the population? And this logic is for this particular situation, fixed computational budget. That means you have given 100,000 function evaluation. When you are given 100,000 function evaluation, do you want to allow your algorithm to converge in 10,000? When you are solving a problem with optimum unknown to you, real world problem. So most of the time you would say, no, I don't want to allow the algorithm to converge in 10,000. I have this much budget. I'd like to continue to search. But within 10,000, you may have the real solution anyway. So can you do maintain the diversity even after finding the good solutions? So that is what you should look for with evolutionary algorithms. But with respect to convergence, I mentioned this. For evolutionary and swarm algorithms, the only thing that we don't want is chaotic behavior. And this one comes in with this flying things, particle swarm and ABC, or the flying things with velocity and motions. You may have chaotic behavior. So we don't want to have chaotic oscillations. That happens when the C1 plus C2 is more than 4.1 or something like that. Then the PSO will become chaotic or something. This another one, I have opposing views. Do you want to have many algorithmic parameters or less parameters and operators? If you ask the reviewers will say it is bad to have many operators and parameters. Can you have an algorithm with almost no operator selection, no parameter selection? Is it possible? No free lunch theorem says it is not possible. When you fix operators and parameters, you have only one algorithm. And the no free lunch theorem says one algorithm cannot solve all of them. So my suggestion is that you should have a flexibility. You should have enough flexibility with parameters and operators. So that is why I say PSO is not so good, because it has very limited tweaking possibilities, only C1 and C2, no crossover. The next point you have to take it, certainly. When you move it to the fly to the next point, you have to take it. So all these things are there. So when you have some freedom with respect to operators and parameter choices, you will be able to tune your algorithm to solve problems with different characteristics. So you come up with optimization problem with different characteristics, and you have some handles and knobs to tune. But you shouldn't be tuning them manually. So you should be looking for adaptive methods. So you need to have some performance feedback based adaptation to tune these operators and parameters when you change the problem. So your algorithm will be flexible and useful as well. So nature inspired algorithms, I don't have much positive comments, because my opinion is it is not good to mimic closely on the natural phenomenon, because natural phenomena, the insects and creatures, they develop their lifestyle or whatever, their capabilities to solve usually one particular problem. Honeybees are just worried about collecting honeys, nothing else. So one particular trait or characteristic, will that be good for solving all sort of problems, all the diverse problems? So personally, I don't think we should go too close to the natural phenomenon, because natural phenomena are very strict. The insect wants to do only one thing, whereas no free lunch theorem says you should have diverse properties to solve diverse problems. So one particular characteristic won't be good for solving all the problems. So there's a conflict I see here as well. And the crossover operator is missing. Dynamic based problems have, as I told you, the velocity forces you to take the next point. You cannot ask the fish or honeybee to reverse back. So that is not there. Whereas the selection based evolutionary operators are better anyway. You compare the fitness and accept or reject. So with this, maybe future direction I go on the tomorrow session, I think. So based on this observation, I have some suggestion how you can develop. So my student is looking at this actually. I put this future direction for the last 2-3 years and I didn't do anything. So only recently I am asking my student to follow these steps. So I have been preaching others, but I haven't asked my students to do these things. So now they are looking at it. So I will share them tomorrow with you, I think. Any questions? 1 or 2 questions?
We have time for questions from the audience.
So the last few slides, anyone disagreeing with me on the last few slides? So these observations are a bit conflicting with reviewers' comments, I think. So.
So especially there are test functions for people to show their proposed algorithm works well. But the thing is, they don't even use the same set of test functions. You know, they pick some test functions in many papers and they show you.
So whenever it comes to me, I tell them that you select one set and select them in full. Don't pick 2 here, 2 there, 2 there, 3 there, and then put them together and show. I immediately send back.
Is that 24 functions?
About 20-30 problems we have collection.
You don't expect them to actually
Do all of them.
do all of them.
All of them.
You want to do all of them.
All of them, yes. For the journal versions, we ask conference, anything okay. And 5, 6 also okay, I think. So it depends how many papers submitted, what is the budget for the organizers. And so you have other things to look at. So if it is going to hit your budget, then you can say whether can it be accepted to save my budget.
So is DE generally viewed as an advanced version of GA and it does a lot better than GA?
So operators are fairly different. So, but it goes through the crossover mutation, selection, and so on. But the operators are fairly different.
But I think the compelling case about PSO is there's a nice story to tell when they do optimization, whereas GA and DE, you just give a mix and finally get the solution. So there's not a
Story.
like a story.
Yeah, that's what I mentioned early on as well, that the swarm algorithms are more attractive to researchers because they can have a narratives with them, I think, a storytelling.
The swarm is the default value seems to work very well, right, for most problems. Seems to be quite amazing.
So practical problems, as I told you, the practical problems come with different difficulty levels. So if you really do a head-to-head comparison with PSO and DE, when the problem difficulty goes up, PSO will lose out rapidly. So if your problem is not so challenging, then PSO will do. The local version can do well, yeah.
Would it be true that if you were to continue to do if the time restores can be very large, if you keep on running, will you in the end get a better solution?
If you have infinitely long time,
Yeah.
the best method is exhaustive search. Nothing is going to beat it. So when you have a time limitation, it is about maintaining the diversity. So if you can maintain the diversity within the budget, say something like you keep the diversity for 80-90% of the time and then release the diversity in the last 20% of the time. That will give you the best chance of looking for the solution. So the diversity control. So within the 80% of the time, you may have found the global solution, but when you solve real world problem, you should assume that you don't know the global solution. So then you control the diversity with respect to the budget, I think. Yeah.
Any more questions? Yes.
One last comment. I think when you think about convergence, you're thinking about the old school classical methods. Nowadays, we are developing a lot of convergence theory for stochastic methods. So I think there can be still some benefit in thinking about.
So population-based stochastic search methods.
Yeah, I mean, you can think about convergence and expectation for.
Simulated annealing has, I think.
Yes.
Simulated annealing has one single point, I think. Is that population-based or the proof is for single point, I think. Is right. Stochastic and the simulated annealing, the basic form is single point, I think. Is right.
But don't you think there is some potential to look at it for multiple particle, population convergence and expectation altogether?
Convergence for these methods, you cannot.
From practical point of view, it maybe doesn't make sense.
So I mean, to prove convergence, you have to go back to the mathematical definitions. Is that right? The gradient zero and all those things. Is that right? Yeah. So, but we don't. We start by saying we are not going to use any of them, I think. And then proof. If you want to prove that, then you have to evaluate them numerically or something like that, and it's maybe possible. Yeah, that's right. But
you are actually making some finite differentiation through some of these algorithms, and we can think combining this information.
usually, all these parameter settings can do quite a bit of things. So as I mentioned to you, the main thing is excluding the chaotic behavior. For differential evolution, there's a scale factor parameter. As long as you keep it below 2 or below 1.5, it behaves finely. So beyond that, I am not too sure what to do. For the PSO, they give the 4.1 as a limiting point. Beyond that, it becomes chaotic. But if you want to go for real convergence proofs, then I think we may have to go back into some of the mathematical concepts, I think. Otherwise, the real global solution may be here, and your population can converge slightly with an offset. It is possible for evolutionary algorithms because they are not looking at the differentials and all those things.
There is still some potential, benefit, I think.
But if you want to force them to go to real mathematically defined solution, then you have to make use of those mathematics, I think. Otherwise, I am not going to tell you anything about gradient, but go to the mathematically defined point. If you ask something like this, I think it's...
Is simulated annealing a very dated version that most in the literature seems to say those things actually doesn't work? In one of the primary examples, we have a proof of convergence.
To the global solution.
On the head, everybody panned it down. Those things actually doesn't work in practice.
No, but I think the proof comes with everything too long, too large. Everything too large, infinite, I think. So how far, they don't say, I think. How long, how far.
Okay, I think people are hungry, so let's adjourn on that. Should I take the speaker again?